we're going to start a lecture, properties of matter. This is our very first thing. So we're going to talk about like what characteristics distinguish different types of matter, like what are the properties of matter, what approaches do scientists use to answer these questions. And so this section is going to talk about matter, physical chemical changes, and then a little bit about scientific inquiry. So chemistry is just the study of matter and the changes it undergoes. So that's what we're going to be doing. We're going to be looking at matter and then just looking at how matter changes. So the first thing we need to figure out is, well, what is matter, right? So matter is anything that occupies space and has mass, right? Like water occupies space, has mass, gold, sugar, air, right? Because air occupies space, right? Air is everywhere around us, and it does have mass, not a lot of mass. Does anybody think of anything that doesn't have matter? Pretty much everything else is matter, so we won't be talking about those things. Radio waves, electromagnetic radiation, yeah, that's very good. But we're actually going to talk a little bit about that. That was a funny one. Yeah, so that's matter. Okay, so now, how do we classify matter? So what we're going to do is we're taking this thing matter, right? Matter, anything that occupies space and has mass. And then what we're going to do is classify it, we're going to break it down. So we're going to break it into a pure substance and a mixture. All right, so we first have anything that occupies space and has mass, and then pure substance, mixture. So again, here's our definition of our matter. So a pure substance has a uniform composition. So it's the same throughout, right? And from sample to sample, it's exactly the same. A mixture has more than one pure substance, and it may or may not have a uniform composition. So let's look at these pure substances and these mixtures a little bit closer. So pure substance, again, has the same composition throughout, and it can be further classified as either elements or compounds. So pure substance, same composition throughout. And we can either classify that as an element or as a compound. So now, an element is anything that can't be broken down on by chemical means. So if you look behind me, I have the periodic table of elements. Anything on this periodic table of elements, that is an element. And these are substances that cannot be broken down into simpler substances, even by chemical reactions. And elements can be separated further into metals and nonmetals, and we're going to look at those. Compounds is another type of a pure substance. These compounds are just two or more elements combined in definite proportions. So for example, if you have an element of carbon and you have an element of oxygen, those are two elements. A compound would be when they are chemically combined. So this would be a compound, CO2, and a definite proportion means it doesn't change. So for example, a CO2 molecule always has one carbon and two oxygens. It never changes. If you change the proportion of carbon to oxygen, if you change one carbon and two oxygens, you have a different compound, right? For example, like CO2 is something like we exhale, plants need it, kind of important for life on Earth, right? But if I change the proportion to one carbon and one oxygen, does anybody know what that is?
Carbon monoxide.
Yeah, carbon monoxide, right? That will kill us. That's very bad. We don't need that, right? And so this is what it means by definite proportions. If you change the number of elements, you change the compound itself, and they're always the same. So carbon monoxide, the properties of carbon monoxide are because there's one carbon and one oxygen. The properties of carbon dioxide are the properties because there's one carbon and two oxygens, and that one oxygen makes a lot of difference. Okay, so here we have our pure substances, and then we have our elements, right? Periodic table of the elements, and our compound, which is just more than one element, chemically combined. Now we can further break these down on our periodic table into metals and nonmetals. And so here's our periodic table. And just move my little zoom thing. So if you look at this, there's this little like, oops, you can see this here. I'm just making this more apparent right now. This little stair step. And if you have a periodic table, if you're in campus, and I would give everyone a periodic table, you can pretty much use any periodic table you choose. But I always suggest having one written out and printed out so you can write all over it because it really helps in chemistry. So this little stair step I've done. So if you can see behind me, hold on, let me try something with my video. I'm going to try and make it so you can see, or you can kind of, now I'm just a lot bigger. But if you can see behind me, which I'm just going to move this. So you guys can see it has a little stair step on there. And so you're going to see, I'm going to actually be using that stair step and just throughout class after I figure out how to make it so you can see my periodic table better. So for right now, here are our nonmetals. And everything else is a metal, right? And so that's how you can tell our metals and our nonmetals. So everything else, so the majority of the periodic table are metals. Now these little green guys here, these green ones are we call metalloids. So they're not like really metals, but they're not really non-metals. They're kind of both at the same time. And so the only other exception to this metal non-metal rule is hydrogen, right? Hydrogen's a gas. It doesn't really belong here. It really just belongs right here. And we'll talk about why is hydrogen right there in the top left corner throughout our class. But for now, just know it's not a metal. It's a non-metal. Okay, so let's go through these. Yes, so when we look at it, yes, 2, 4. So all you're doing is looking at that periodic table. Aluminum, 8, lead, and tin. Those are all of our metals, and everything else would be a non-metal. Yes, very good. Okay, so now let's look at atoms. So atoms, so matter is composed of atoms, and atoms are those things on the periodic table that we just talked about, right? The atom is the smallest unit of an element that retains the chemical properties of that element. Okay, so what does that mean? So if we think about an atom, so does anybody remember atoms are made up of, what's in an atom? Oh, I already saw it, yeah.
Protons,
neutrons,
electrons,
yeah, and a bunch of other things. We're only going to talk about protons, neutrons, and electrons. So let's say we have 2 atoms. Let's say we have like a carbon. Actually, let's just, we'll do carbon and iron. So carbon has protons, neutrons, and electrons. Iron has protons, neutrons, and electrons, right? But the only difference between, so a proton of carbon is exactly the same as a proton of iron. They are identical. Same thing with the neutrons, same thing with the electrons. It's the different numbers of protons, neutrons, and electrons and how they're arranged, which gives carbon its properties. Same thing with iron. So what an atom is, it's the smallest unit that retains the chemical properties of that element. So although we can break carbon down into protons, neutrons, and electrons, and we can break iron down into protons, neutrons, and electrons, to have the properties of carbon and the properties of iron, the atom is the smallest amount we can do it. So for example, if you had oxygen, like oxygen is a gas, right? If we break it down further, then it's no longer a gas. It's just protons, neutrons, and electrons. Okay, so now when we look at atoms, if we combine more than one atom, we create molecules. And a molecule is just, again, 2 or more atoms in a specific arrangement, like our CO or our CO2. And they can be from same elements or different elements. So for example, this right here, this is O2. So that's just a molecule of O2. And this is a molecule of CO2. So there's that 1 carbon, and then there's 2 oxygens. And so a molecule is just more than 1 atom. Now, a compound is, again, a pure substance that has two or more elements chemically combined in definite proportions. Now, specifically, what does this mean, chemically combined? Okay, so if you've ever heard of fool's gold looks like gold, but it's not. It's actually iron pyrite. So fool's gold is iron and sulfur. So it's iron and sulfur, but it's chemically combined. So they're chemically combined together and they're bonded together. And together, when they're chemically combined, they actually look like gold. Now, if you just had some sulfur, so in this is sulfur, and these are iron shavings right here. So if we just put like a bunch of iron and a bunch of sulfur in a bowl, all we have is a bunch of iron and a sulfur in a bowl, right? That's a physical combination. That's not a compound. The compound has to be, again, chemically combined in a definite proportion, meaning, again, to be fool's gold, it's always 2 irons and 3 sulfurs, right? That's, again, what we mean by those definite proportions. And the compound has different properties than its chemical components, right? And so I always just, one example of this one is like water, right? What do we know about water, right? We swim in it, we need it to, right? We need it to live because we have to drink it. If you breathe it, you drown, right? And so water is just H2O. But water is made of oxygen and hydrogen. So if we look at hydrogen or oxygen, so let's look at oxygen because we know what oxygen is, right? It's in the air, right? We need it to breathe, right? If we don't breathe oxygen, we die, right? If we breathe water, we die, right? And so the compound has different properties than that of its element, right? And so when we have water, the hydrogen, 2 hydrogens and 1 oxygen chemically combined, it has different properties than the individual elements themselves. And that's what we mean by a compound. So sand, so anybody who's ever had sand, right? Oh, great question, Danielle. Is there a difference between a molecule and a compound? A molecule is just more specific. It's 2 nonmetals, which we'll talk more about that probably in a couple of weeks, where a compound is just any 2 atoms combined. But if you interchange the 2, it's fine. At this point in time, it's okay if you interchange those. Okay, so for example, sand is just silicon dioxide. There's always 1 silicon to 2 oxygens. Right? So what does the formula say? 1 Si and 2 Os. So whenever we have that chemical combination, that's going to be silicon dioxide, which is sand. Okay, so now when we describe matter, we have these 2 words that for some reason are very difficult for us to remember. So make sure you circle these words, highlight, so you don't forget them. So the first one is an extensive property. It depends on the amount of matter in a sample. So this could be like mass, volume, calories. The next one is an intensive property. This depends on the type, not the amount present. Hardness, density, boiling point. I like to use donuts as an example here. So if you eat 1 donut, or if you eat 12 donuts, you're definitely going to notice a difference. Right? That's an extensive property, right? The amount of donuts, the number of calories between 1 donut and a dozen donuts, big difference, right? You will feel that difference. Now, an intensive property of a donut is that it's soft. So if you had a dozen Krispy Kreme donuts, sorry to make you hungry, they have the same, they're both, all 12 are soft, right? All 12 are shiny, right? That's an intensive property. It depends on the type of matter, not the amount. So if you had 12 donuts or if you had 1 donut, you would describe them the same way. But if you ate 1 donut versus eating 12 donuts, those calories definitely depend on the amount, right? That's an extensive property. So intensive versus extensive. Another thing we need to look at here, and we'll get to this more when we get to our gases chapter, but I just wanted to bring it up now, just so you know the difference between direct and an inverse relationship. So all of you have probably had math, and you might have heard these things, but you might have forgot them. So The first one is a direct relationship. How can you tell if a direct relationship? So in a direct relationship, you get a positive straight line like this. So if one goes up, the other one goes up. So if you have 4 and 1, so if 4 doubles to 8, 1 doubles to 2. So if one goes up, the other one goes up. That's a direct relationship. So a direct relationship, one increases, the other increases, or one decreases and the other decreases. Now, an inverse relationship, this next one is an inverse relationship. When one increases, the other one decreases, right? And this graph is no longer straight, it's not linear. It's kind of this little kind of backwards J shape or lazy L shape, right? And so that's how you can tell if it's an inverse or a direct relationship. So just make sure you know direct both increases, inverse one goes up, the other one goes down. And remember the shapes of them because we're going to be using this principle a lot in introductory chemistry. Okay, so now let's look at these. So which one of these are elements? So feel free to say it or you can type it in the chat. Which one of these are element? 1 and 4. Very good. You guys are fast with these. Right, so 1 and 4 are our elements. The other 2 are compounds. Pretty easy to see because the compounds are just more than one piece, right? More than one element. So element, compound, element. And so you can see if you have your lecture notes, you can just like fill that in and it kind of just helps guide you through the lecture itself. Now mixtures. So first we had matter, and we said matter, anything that occupies space and has mass. And then we said pure substances. And pure substances, we did elements and compounds, right? Element from the periodic table, compounds, more than one element, right? Now on the other side, we have mixtures. So mixture, so we have matter, pure substances, mixtures. So it's on the other side. So mixture, and I'll show you a picture of that in just a second. This is a combination of 2 or more elements or compound, but these can be separated by physical processes. This is like pencil lead, salt water, air. All of these they're easier to separate. For example, if you had salt water and well, let's say you were at the beach, right? And you had water on you, the water evaporates, but the salt is always left over, right? And so you just let it evaporate. And that's how you can separate salt water, much easier. So when we look at our mixtures, so a mixture is just 2 or more pure substances physically combined, right? And so we have 2 different types of mixtures. We have homogeneous mixtures, well, those have the same composition throughout. So for example, if you had Gatorade, which I always forget to grab one of my son's energy drinks when I come up here. So if you look at the ingredients on the Gatorade, there's like water, sugar, color, sodium chloride, right? All these things in that mixture of Gatorade. But if you look at that Gatorade, if you look at the top of it and the bottom, they look the same, right? So that's a homogeneous mixture because it has the same composition throughout. Now, a heterogeneous mixture does not have the same composition throughout. And so you can actually see the difference. So if I had like sand and water, right? If you were at the beach and you had a bucket of sand and water, that would be a heterogeneous mixture because you can obviously see the difference between the sand and the water. So they do not have a uniform composition throughout. So when we look at these homogeneous or heterogeneous mixtures, so I have to be very specific on these. So if I said beautiful, clean salt water that looks the same throughout, that would be a homogeneous mixture. And again, this depends on if there's suspended solids. Like if I said like salt water from the ocean, then you might go, that's a heterogeneous mixture, right? Because there's like kelp, fish poop, right? All sorts of things in ocean water. Lake water is, let's say it's beautiful, clean lake water, right? That again would be a homogeneous mixture because it's the same composition throughout. Tap water, again, there could be some arguments on this, but let's say we had beautiful, clean, pure tap water. then it would be a homogeneous mixture. Air. So if you look around you, you can't see the air, right? That would be homogeneous mixture. Except like when there's Santa Anas, right? When the Santa Ana winds blow, and have you ever looked over like the ocean or towards the ocean and you see this nice brown layer of air, right? That would be a heterogeneous mixture because you can actually see the differences in the air. Brass. Brass is a homogeneous mixture. You probably see brass if you've ever been on a boat. It's kind of like shiny gold looking railings. That would be brass. Potting soil. Okay, so a lot of people are like, what does potting soil look like? It's brown dirt with little like white circles in it. So you can see the difference between the brown dirt and the white circles. That makes it a heterogeneous mixture. Now, cake mix, again, some people are like, well, I'm not sure. Chocolate chip cake mix, right? You can see the chocolate chips versus the rest of the cake, then that would be a heterogeneous mixture. And so, again, those heterogeneous mixtures, you can see the difference in what we call different phases. Like if you had a chocolate chip cookie, you can see the chocolate chips and then the rest of the cookie is a distinct difference. And that's a heterogeneous mixture. Okay, so now let's look at everything we've talked about. Matter. Anything that has mass and occupies space, right? So, oh, good question. Smoke, heterogeneous, yeah, because if you see smoke, like the fires that are around here, yeah, because you can see a difference between the smoke and the air, so that would make the air being a heterogeneous mixture. So right now, I don't know if you can smell smoke where you are, I can't smell it right now, but that changes on the hour, right? So when you can smell smoke and you can see it, that is a heterogeneous mixture. Or if you're anywhere in Northern California, they can't even see the sun right now because of all the smoke. Okay, so matter, anything that has mass and occupies space. Now, can it be physically separated? So if the answer is no, it's a pure substance. And if it's yes, it's a mixture. And now remember, pure substances can be broken down into elements and compounds, right? And further elements can be broken down into metals or non-metals. And then we're not even gonna worry about graphite. Just ignore that one. And our mixtures, if it's the same composition, it's a homogeneous mixture. Now we call these homogeneous mixtures solutions. And you can have, a lot of time people are like, oh, solutions, that's a liquid. Not necessarily, right? You can have a solid solution, like a brass railing is an alloy of two metals, or air, well, clean air, right? So clean air, right? Because in air we have like carbon dioxide, oxygen, right? We have argon, all sorts of things in the air. So it's a solution. So solutions can be solids and gases also. If it is not the same composition throughout, then it's a heterogeneous mixture. It's just like our chocolate chip cookies, or like, have you ever had those boba drinks, like with the little balls at the bottom? That would be a heterogeneous mixture. Or orange juice with pulp, that would be a heterogeneous mixture. If you can see the difference, if you can see things in the mixture itself, that's heterogeneous. Okay, so, well, we just did this one. I just told you that air, right? Air is a mixture because it's a pure substance. How about soda? Is soda a pure substance or a mixture?
Mixture.
Yeah, it is. It's a mixture, right? Because think what's in soda, right? Sugar. Oh, we'll say ingredient number 1, sugar. Ingredient number 2, water, right? Maybe water is number 1. Coloring, right? If you're Dr. Pepper, you have 24 different types of flavors in there. So that's a mixture. Distilled water. So distilled water is, well, if I tell you, you'll know, it's pure water with everything else removed. So it's obviously going to be a pure substance. So if soon, hopefully, if you ever take a science class on campus at SAC, we have distilled water, we call it DI water, deionized water, in all of the labs there. And the reason we do this is because, and you've probably experienced this, when you get your car washed, and if you don't dry it fast enough, there's little like spots all over it. Those spots are because in water naturally there's salts in the water. just like salt water. They're not the same, but the salt's in the water, and the water evaporates and it leaves the salts behind. And those are those super annoying spots if you don't dry your car fast enough. Those are salts. But if you have DI water, there's no salts in it. So if you ever get your car washed and it has like the no spot rinse at the end, what that is distilled water. And so they're spraying distilled water and they've removed all the salt out of the water. So then when it evaporates, it doesn't leave those annoying little circles, those spots all over your car. You can't really get enough from the lab to wash your car, but if you could, you'd have a spot-free car. Okay, a diamond. So a diamond is just carbon. And so it's a pure substance, right? Because it's just carbon, just all bonded together. And we'll actually look at carbon probably one of the last days of our class. Okay, so let's practice this. So element, compound, or mixture. So of these, we'll just do one at a time. Carbon dioxide, what do you think?
Compound.
Compound. If you want, you can just do like E, C, or M, so you don't have to do the whole thing. Yeah, it is indeed a compound. How about nickel? Yeah, very nice. Nickel's easy. It's on the periodic table. And if you're watching this later, make sure you're doing this also. Vinegar. This one's a little trickier. But yeah, it's a mixture, right? Mixture, vinegar is acetic acid, and it's water together. That one's a little trickier. Water. Yeah, that one's not so hard, is it? Pure water. Very good. So pure water is indeed a compound. Okay, fluorine. What is fluorine? Yeah, fluorine is an element, right? Because you just look at the periodic table, and that's how you can tell. How about table salt? Yeah, table salt, believe it or not, is just sodium chloride. So it's actually an element. And we're going to talk about why we call this table salt very soon. It's because all ionic compounds are salts, but this one we use all the time. So it's a compound. How about soap? Yeah, you're like, if you have to ask, I don't know what's in it, it's probably a mixture, right? If you're not sure what's possibly in there, it's a mixture. Seawater. Same thing, right? What is in seawater, right? Fish, kelp, right? Definitely a mixture. Sand. Okay. So that's our element, compounds, and our mixtures. So now we're going to classify this as a pure substance. And so, or a homogeneous mixture or a heterogeneous mixture. So gasoline. So a lot of people are like, I've never seen gasoline. How would I know? Well, so you can guess. What do you think gasoline is? A mixture? Yeah, it actually is. It's a homogeneous mixture. So gasoline, and it has a lot. So even if you didn't know this, I would obviously give this to you in a quiz without talking about it first. So gasoline has a lot of different compounds in it, and they're just physically blended together. And if you saw gasoline, it looks the same throughout. So that's why it'd be a homogeneous mixture. How about a stream with the gravel on the bottom? Yeah, heterogeneous mixture. And the reason it's a heterogeneous mixture is because you can see a difference between the gravel at the bottom and the stuff that's on the top, right? And so that's why it's a heterogeneous mixture. Okay. And our last one, copper metal. What is copper metal? Yeah, it's a pure substance. And the reason it's a pure substance, again, is because it's an element. And pure substances can be broken down into elements and compounds, hence a pure substance. Because all elements and compounds are pure substances. Okay, so now we talked about these mixtures, and we said that the mixtures could be separated physically, but then I never told you how we can separate them physically. And so we're actually going to be doing some of these in lab, which again, we'll talk about in a couple weeks. So how do we separate mixtures? So we have a couple different ways. We can use what's called distillation, filtration, chromatography, or evaporation. So distillation actually, here I'm going to show you, let's do filtration first, because that's the first picture I have. So we actually are great with filtration. Just think coffee, right? How do you make coffee? You have coffee grounds, you have water, you have a filter, right? And now the reason you have a filter is so you can separate the coffee grounds from the water. Same thing, that's what filtration does. And so if you have a mixture of a liquid and a solid, like our coffee grounds, you have a filter, which here's your coffee filter, and then the only thing that comes out is the liquid component, and the solid component stays in the filter, right? And you know, if you get a hole in the filter, then the solid component, aka coffee, comes down and makes you very upset, right? And so that's filtration. And so that helps us usually separate between a solid and a liquid. The next one we have is kind of, it's filtration and what we call distillation. So if we had a mixture of, let's say, well, sand, salt, and water, we could filter it like we do coffee, and we could get our sand out. But then we would still have a saltwater solution. So what we could do is we could either just let it sit there for a really long time, and eventually all the water would evaporate. So we could use evaporation, or we could use what's called distillation. So here's distillation, and this is actually really fun to do, but we won't be able to see it in class because we're not on campus. So with distillation, how it works is you have, for example, here's your salt water, and you heat it up with a Bunsen burner until it boils, and then you have this condensing tube right here. So this condensing tube goes all the way through here, but around it on the outside is like another glass tube. It's like an isolated glass tube, and water goes into this tube and kind of circles the outside of the tube and keeps it cool. So what happens is it boils here, but then it gets cool here and it condenses into liquid. And so what's happened is you can actually boil your water and your salt will stay here. And at the end, all you have left is salt here and water here. So this uses boiling points to separate two liquids. This is actually quite fun with Cherry Coke because you get like 6 different things coming apart at different times. And so you end up like 6 beakers of goo. It actually looks like goo from Cherry Coke. So when we look at how we can separate it, we have distillation, which uses boiling points. Filtration, which uses like, you can separate the solid, the states of matter. Evaporation just says volatility means does it evaporate. And then chromatography, we're not going to talk about that one that much, but this one actually, if you've taken biology, you'll do a lot of chromatography. If you take 210, a lot of chromatography in that also. And that's just using adherence to surfaces, what we call difference in their polarities, which we're not going to talk about until the last week of class. Okay. So now when we're looking at this, we're looking at different ways we can represent water. And I just wanted to show you different things you're going to see in class. So here's like, for example, how I wrote water. By the end of class, you're going to be able to see it just like this by the end of the semester. Sometimes we write it like this. So here's our O and our H. And then we have a space filling model, which kind of better depicts what the molecule looks like. So you're going to kind of see it, that's the O, H, H. You'll see kind of all 4 of those throughout the course, but I just wanted you to kind of get an idea of what it sometimes looks like when they're different. Okay, so we're gonna do one more thing and then we'll stop for today. So we're gonna look at these as an element, compound, mixture, element, compound, or mixture. So I'm going to have you guys, so you can just do like, oops, is a mixture of elements, right? So we can just say it's a mixture. D again is a mixture. This time this is an atom, right? And compound. And E is also a mixture, right? And so I didn't have you say it's a mixture of elements or compounds. But how can you tell it's a mixture versus a compound? So you see how, like, for example, for C, these are not chemically combined. They're just sitting there together. They're not actually bonded versus like here, these two are actually bonded together. So this is what this looks like. This is a compound, right? Here's our compounds right here. A mixture is they're not chemically combined. So here's one thing and then three other things that are different. That's why it's a mixture. Okay. So, all right. So I said, why is it two or more different elements or two or more elements? So you could have called this one a compound or a mixture. I mean, sorry, not a mixture. A compound or you could have called this an element. An element, usually we call it one single atom. A compound is more than one. So I would have counted both of those correct, element or compound. Okay, so we're gonna end today. I wanna make sure that everyone